Functions and Relations Part 2. In the Part 1 video, we discussed relations, functions, and we started discussing one-to-one and onto functions. We will continue in this video with functions one-to-one and onto, and then we'll go on to Stirling numbers. We will skip the special functions in your book and go on with Pigeonhole Principle, and finally we will look at function composition and inverses. First, a quick review. The Cartesian product, A cross B, is equal to the ordered pairs AB, where A is an element of the set A and B is an element of the set B. A relation, A on B, is any subset of A cross B. A function is a special type of relation from A to B in which each element of A appears exactly once as the first of an ordered pair. A function that is one-to-one is a function where each element of B appears at most once as an image of A. A function is onto if the image of A is equal to the set B. Some pictures for those examples. This first picture here, we have a mapping from set A to B, but this is not a function because you can see the element 4 in A is mapped both to the element 2 and -2 in B, so it is not a function because it is not well defined. For it to be a function, every element of A must appear exactly once, and here it appears twice. Our next picture shows a one-to-one and onto function. So it's one-to-one because every element of B appears at most once. It is onto because every element of B has something mapped to it. Our next picture is a function that is one-to-one but not onto. So it is one-to-one because every element of B appears at most once, but it is not onto because it has an element that is not mapped to at all. This function here is not one-to-one, but it is onto. So it is a function because every element of A appears exactly once, but it is not one-to-one because there is an element of B that appears twice. And to be one-to-one, it has to appear at most once. It is onto, though, because every element of B has something mapped to it. Last, we have a function that is neither one-to-one or onto. So it's not one-to-one because here we have an element of B that appears twice. And it is not onto because here we have an element of B that does not appear in the relation at all. So that concludes our quick review of relations, functions, one-to-one, and onto. So we're ready to go on with Stirling numbers. First, we have this observation. The number of onto functions from A to B, where the cardinality of A equals M and the cardinality of B equals N, is the number of ways to distribute M distinct objects into N distinct containers with no container left empty. Again, this is an onto function. We can illustrate this some with a picture. Let's say we have a set A, and let's say the cardinality of A is equal to 4. So we have 4 elements, and they are distinct elements. Then we have elements in set B. Let's say the cardinality of set B equals 3. So B has 3 elements, and they are distinct elements. So the number of ways I can map each element of A onto B is the number of ways basically I can put these elements, I can consider these elements as putting these elements into containers. Here's 1 container, here's 2, and here's 3. So there are many ways I can put them onto the container. But if I do the number of onto functions, which every element of B is hit, that's equivalent to saying no container is left empty. So we'll see this idea here is related to our Stirling numbers, which is here. The number of ways to distribute m distinct objects into n identical containers with no container left empty is the Stirling number, S of nm, which is equal to this number here, which fortunately we don't have to calculate, so don't even bother remembering this. The formula is in your book if you'd like to look at it, but I wouldn't use it. Instead, we use these tables, which I have reproduced part of this table from your book, and it's on your handout that you're allowed to use on your exam. So here are the Stirling numbers. It lists a partial table of Stirling numbers. So first we'll zoom in on the Stirling numbers. So the way we read this table is m is in this column and n is here. So if we want to look up S of 7, 4, which again is the number of ways to distribute 7 distinct objects into 4 identical containers, we would look down the row 7 and 4 and we'd see it would be 350. And now to relate the Stirling numbers back to this original problem, the number of onto functions from A to B, where we distribute m distinct objects into n distinct containers with no container left empty. So for the cardinality of A is equal to m, which is greater than cardinality of B, which is equal to n, there are n factorial s, m, n onto functions from A to B. Essentially, what the difference between this first idea and the Stirling numbers is the first idea has distinct containers, whereas the Stirling numbers has identical containers. So in order to make these identical containers distinct, we order them, and that's this n factorial. So our first example is, how many ways can I distribute 7 different colored balls into 4 identical containers with some containers possibly left empty? Our first step is to consider possibly left empty. We're going to have to do this in cases based on how many containers are left empty. So there's either no container left empty, or 1 container, or 2 containers, or 3 left empty. It's not possible to have all 4 containers left empty because otherwise there's nowhere for the balls to go. So since the containers are identical, these are Stirling numbers. So none left empty, I am going to distribute 7 balls into 4 containers. Or I will distribute 7 balls into 3 containers, or 7 balls into 2 containers, or 7 balls into 1 container. I have showed you on the previous slide how to look up S of 7, 4. We can use the table to look up 301 for S of 7, 3, and then we have 63 plus 1. So this is our final answer. Some more examples come from your chapter introduction, so I'll let you look at them. There are 4 examples there, but I will give you 2 here. And they all have they're all based on the same answer, which is S of 7, 4. The first one, how many 7-symbol quaternary sequences, quaternary are made up of 4 symbols, 0, 1, 2, and 3, have at least one occurrence of each of the symbols 0, 1, 2, and 3. So again, we're thinking about having 7 symbols, and we're going to map them onto one of our 4 symbols. Okay, so possibly the first one might be a 1, the second one might be a 3, etc. But how many ways can we do this so that we're mapping all 7 distinct symbols into distinct symbols here, at least one occurrence of each of the symbols, meaning no container left empty. So that's going to be our 4 factorial. Our 4 factorial. That's to take into account now that our containers want to be distinct. S of 7, 4. The next example, we have 7 unrelated people enter an elevator which goes to 4 additional floors. What is the probability the elevator must stop at each floor to let a passenger off? Since this is a probability, the total number of ways these 7 people can get off the floors is 7 to the 4th power, because each person can choose one of 4 floors. But how many ways can these are distinct people, get off of 4 distinct floors such that the elevator must stop at each floor? So this is an on-to function because every floor is hit. Again, the 4 factorial is because the floors are distinct, and then we have s of 7, 4, divided by 7 to the 4th. So now we've completed our functions, our one-to-one, onto, and Stirling numbers. Again, we're going to skip the special functions, which means we can continue with the pigeonhole principle. The pigeonhole principle is actually quite an easy idea. If there are m pigeons occupying n pigeonholes and m is greater than n, then at least one pigeonhole has 2 or more pigeons in it. And in case you are not familiar with pigeonholes, not that I've ever really seen one except maybe in movies, pigeonholes are like these little cubbies that you can place pigeons in. And as you can see, all of our cubbies right currently are occupied and one more pigeon comes in, so there's more pigeons than there are cubby holes. So if he wants to stand in one of the pigeonholes, one of these pigeons is going to have to share, and they'll be really close and crowded together. And in terms of functions, essentially we're mapping these pigeons into pigeonholes. And if it happens to be we have more pigeons than pigeonholes, then when we do our mapping, at some point, our last pigeon is going to have to find an already occupied hole to crowd into. An easy example in mathematics, a drawer has socks in red, blue, black, and green. Without looking, how many must be drawn to ensure a matching pair? In this case, we think of our pigeons are the socks, and our pigeonholes are the colors. So we have red, blue, black, and green. We have 4 colors. So how many socks do we have to have in order to ensure that one of these cubbies has to have 2? Well, you basically need m greater than 4. So if we have m equals 5, that's the smallest number, we can guarantee that after we draw one of each color, this last sock has to repeat to color. So the answer is m equals 5. Our next example I used to not like because I thought it was so contrived, but I have seen actually in mathematical proofs, not in people playing chess, not in taking medications, but in mathematical proofs something similar. So I've added this example back in. By the way, this PHP is Pigeonhole Principle. So the example problem is, a chess player wants to practice in a 77-day period. He wants to play at least 1 game per day, but no more than 132 games total. Show there will be a sequence of consecutive days during which he plays exactly 21 games. So just a word on what this problem means. It means that there's going to be a sequence of days. Maybe it's day 3, day 4, and day 5. During these 3 days, the sequence of days, in other words, the days have to be consecutive, he plays exactly 21 games. Maybe he plays 7 each day, maybe he plays 7 on one day, 5 on the other, and then to make it up, he has to play 9 on the next. Whatever it is, there is a sequence of 3 days, in this case, where he plays 21 games. I'm not sure if the sequence is 3, but essentially we're going to show there is a sequence of consecutive days during which he plays exactly 21. So we're going to start by looking at our sequence A1, A2, up to A77. That's the strictly increasing sequence where A sub I is equal to the number of games he has played up to the ith day. Note that A77 is less than or equal to 132. So again, if A1 is the number of games he's played on the first day, A3, for example, is the number of games he has played up to day 3. So it's all the games he's played in day 1, day 2, day 3. That would be A3 is equal to the games played day 1, 2, and 3. And as you can see, it's a strictly increasing sequence since he plays at least 1 game per day. So now we're going to look at this strictly increasing sequence, which is our original A sub 1 up to A77, along with a sub 1 plus 21, a sub 2 plus 21, all the way up to a 77 plus 21. So this is a strictly increasing sequence, but also within we have this strictly increasing sequence and this strictly increasing sequence. So you will notice the values of the strictly increasing sequence range between 1 on the first day and 132 plus 21, because remember, he's going to play at most 132 games, no more than 132 games. And then if that's the maximum plus the 21. So there are basically 2 times 77 values. In other words, there's 77 a sub I here and 77 a sub I plus 21. There are 154 numbers, but only 153 values. The 153 comes from the 132 plus 21. So I should just write that down. That's 153 over here. Which means, since there's more numbers than there are values, that sum a sub I is equal to a sub j plus 21. So I corrected this. So there's some a sub I that's equal to a sub j plus 21, where I does not equal to j. In other words, because these values are strictly increasing, none of these can equal each other. These values are strictly increasing, so none of these values can equal each other. So it must be one of these values is equal to one of these values here. And that's what this is saying. Sum a sub I is equal to sum a sub j plus 21. And these are the days, the ith through the jth day, that exactly 21 games are played. So take a minute to look at it. It's an interesting proof, but not something that's immediately obvious. One more example, which is really interesting because it's in a proof, so it's not contrived, or it's not like you're looking for socks in the dark. In chapter 6, section 6.3, there's an example, 6.23, that uses the pigeonhole principle in a proof. So now we've covered the pigeonhole principle, and we're ready to go on to function composition and inverses. So a definition of function composition. If f is a map from A to B and g is a map from B to C, then we can define g composed of f is a map from A to C, and we can define it also equal to g of f of x for all x in our starting set A. A picture for that idea, so we have a function f that goes from set A to set B. We have a function g that goes from set B to set C. So we can compose our function. We can do f of x first to go from A to B, and then g to go from B to C. So essentially, we go from A to C. Examples of function composition. Our first one, we have f and g are functions from real numbers to real numbers, where g of x is equal to 1 minus x plus x squared, and f of x is equal to ax plus b. We can look at f composed of g of x is going to be f of, and now we're going to plug in g of x here, f of 1 minus x plus x squared, which is equal to a times 1 minus x plus x squared plus b. I can compare that to g of f of x, which is equal to g of, now I'm going to plug in f of x over here, g of ax plus b, which is equal to 1 minus ax plus b plus ax plus b squared. Which brings us to a general note. In general, g of f of x does not equal to f of g of x. Another example where we have g is the function from the natural numbers to the natural numbers, where it takes an integer n, and it maps it to 2n. And f is the function that takes the number 2 and takes the number 1 and maps it to the number 2. So we can do g of f of 1 would be g of an f of 1. F takes 1 and maps it to 2, so that'll be 2, which is equal to 4. We can compare this to f of g of 1, which is equal to f of, and g of 1 is going to take 1 and multiply by 2, so that's 2. And here, f does not define anything for 2, so this is undefined. So now that we've discussed function composition, we can talk about inverses, but first we have a definition. The identity function, which I'm going to denote with the 1 sub a, maps from a set A to a set A, and it's called an identity function if for every element A in the set A, the identity function maps it back to itself. We also have the idea of an inverse. So G is the inverse of F, and we denote that with G is equal to F raised to the negative 1. If F goes from A to B, and G goes from B to A, and G composed of F is equal to the identity function, and F composed of G is the identity function. So the idea of the inverse is it kind of undoes what the function does. So if f of x maps x somewhere, G undoes it and just gives you back the original identity. Same for the f of g of x. We'll do a couple of examples, but one more theorem. If f is a function from A to B, f is invertible. If and only if f is 1 to 1 and onto, and what invertible means is it has an inverse. So you can kind of get a feel for this intuitively with a drawing. If you're mapping from A to B, a function f maps from A to B, it needs to be, if you want to be able to then go back from B to A with f inverse, such that you come back to the identity, essentially you want from every element of A, you want it to map to exactly 1B. Otherwise, it won't be defined when you're mapping back from B to A. And also you want it to be onto, because when you're mapping back from B to A, you want that function to be well defined. So our first example of function composition and inverses. So f is the function that maps x to y such that they lie on this line, 2x plus 3y equals 7. So in our domain and range, f goes from the real numbers to real numbers, so we can plug in real numbers for x and y. If I want to find the inverse, it's actually not that hard. F inverse is going to equal to our x and y pairs such that 2y plus 3x equals 7. So all I did was swap the x and the y, essentially because if I'm over here and I map this x to this y for an inverse, so in other words, if in f I have x goes to y, essentially for the inverse, what I want is I want my y to go to my x. In other words, I'm just swapping my x's and y's. To formally prove this, I could say I'll take my original f and I can write it in this form. 3y is equal to 7 minus 2x. Y is equal to 7/3 minus 2/3 x. I can take my f inverse, and again I can write it into the form y is equal to 1/2 7 minus 3x. And then I can see what f inverse of f of x is equal to, and hopefully I get back my x. So I have f inverse of 7/3 minus 2/3 x, which is equal to, now I'm plugging this value into here, which is equal to, this is equal, 1/2 7 minus 3 times 7/3 minus 2/3 x, which is equal to 1/2 times 7 minus, and in this case, the 3's multiply, and I'm going to have minus 7 plus 2x, which is equal to x. And I can do the same thing, f of f inverse of x. I'll leave that as an exercise for you. Furthermore, if I want, I can also ask to show that I can note that f is 1-to-1 and onto by our theorem. And I'll leave that to you as well, as since earlier in this chapter we had talked about how to prove things were 1-to-1 and onto. Our next example, we have the function f, which is gives us the ordered pairs such that y is equal to x to the 4th plus x. F goes from the real numbers to the reals. I can start by trying to compute an inverse, but I am going to stop for a moment and just say there's no inverse. And we know this because f is not 1-to-1. In particular, f of 0 is equal to f of -1. In other words, f of 0, f of 1, if when we plug in f of 0, we get 0 plus 0, so that maps to 0. And f of -1, when we plug that in, we get 1 to the 4th is +1. I'm sorry, there should be a negative. And then when we add it to our -1, we also get a 0 here. So this is why functions have to be 1-to-1, because when we try to map back the inverse, now our function is no longer well defined. So now we've covered the basics of function composition and inverses. And that's all we have for this chapter. So thank you for listening, and I'll see you in class.